So here we go with doing the actual calculation part of these then. I've went back in and I've added some numbers on a couple of them. I've redrawn the diagrams just to clear things up. If you need to do that, certainly pause, take a moment to do that. And I always recommend that you pause the video and work ahead of me, or at least when I get things set up, work it out yourself and then double check your answers rather than just following along here. But we're going to ask two questions on all these. What is the magnitude for each force vector? So every arrow that we draw, we're going to come up with a size of the force vector there, and then what is the net force, if there is a net force. Of course, a few of these we've already established that the net force is 0, and that's okay. So here with our object on our ground, we have I just gave it 500 grams and just explicitly stated that it's at rest. So if we want to solve for the force due to gravity, that is any force is m times a, but in this case, since we're dealing with gravity, it's the special case of a, the acceleration due to gravity, g. So then from there, it's just plug the numbers in. Now, we have to be careful here. We're using the MKS system, or variation on the metric system, where all of our masses have to be in kilograms. So that's going to become 0.5 kilograms. Just move the decimal 3 to the left, or divide by 1,000 to get grams into kilograms, but that's one you should just know. Anyway, but 0.5 kilograms, and then that's going to be times 9.81 meters per second squared. And so now I get 4.905. I should have been able to do that in my head. I've done this one a bazillion times, and that would be kilogram meters per second squared. That, of course, is acceptable as a unit. However, 3 sig figs here, we should round this one off to 3 sig figs, so I get 4.91, and kilogram meters per second squared can be abbreviated as Newton. So that's equal to our force due to gravity, and then our force, the support force, the normal force, must also be 4.91 newtons, and the directions here matter, equal in size, opposite in direction, which is why they cancel out and give us a net force of 0 newtons. Next problem here, I decided to go ahead and cancel out a resistance for our calculation here, so we only have this now, and we have a 1 kilogram ball, and if it's 1 kilogram, then we just need to solve for the force due to gravity, and the force due to gravity is, again, just m times g. So 1 kilogram times 9.81 meters per second squared, and that gives us 9.81 newtons, 2 sig figs, 9.8 newtons. And then that would be our net force, 9.8 newtons, but we have to explicitly state our direction here, down, or we could draw an arrow to show that. But when we're solving for a net force, we need to include that direction there. Or we could label it here where it would be obvious, but if you're asked to explain the net force, show the net force, you need that as a separate statement. You need to make sure you have direction. I consider those directions as part of your units. Now, yes, we could get into using signs for directions, but if you're going to do that, put the positive for positive ones or put the negative, because otherwise I don't know for certain if you mean that. Of course, it depends on whether we consider gravity to be positive or negative, because it's really just a matter of which way we turn our coordinates, whether we assume that up is the positive direction or down is the positive direction. We've done both. Normally in my test I say assume gravity is 9.81, in which case down would be the positive direction. I decided to clean this one up a little bit. We'll draw the force arrows back in here as we need it, but I got rid of the table. So here we have our a 0.1 kilogram block, and so then it, of course, is going to feel its weight. It's m times g, 0.1 kilogram times 9.81 meters per second squared. And so then that's just going to come out to be 0.981 newtons, and again with sig figs we're going to round that off to 0.98 newtons down. That means that the tension up has to be the same, which means that this block over here, if I draw it as a free body diagram so I don't run out of room, is feeling a tension of 0.98 newtons to the right, We have this one as 0.2 kilograms. I could set this up here again. Rather than doing that, I'm just going to double this, because if it's 0.2 and this was 0.1, then its mass is double, its weight is going to be double. So it should come out to be 1.96, but yeah, 1.96, and that would be newtons down and 1.96 newtons up. So then those two are the same, and then these two here are the same and are equal to that one. Now, the other thing you're commonly going to be asked here is, what is the acceleration of the sliding block? Actually, of the blocks, because it doesn't matter, because if this one's moving at a certain rate, then this one's going to be moving at the same rate. So anyway, let's go ahead and solve that one. So now what we know is we have a net force. This one here is net force is 0.98 newtons to the right for the top block, and it would be, if this block is accelerating at that rate, then this one here is also going to be accelerating at the same rate. So anyway, from here we can go F equals ma. And this time we have a force, and we're not using the acceleration due to gravity for once. So far it's looked like all these problems are the same because we keep using mg, but this one here we finally get to do something different. So this is our net force. Our mass this time is actually the combined mass of the two of them, so that's going to be 0.2 plus 0.1 kilograms times by the acceleration, which is what we're interested in solving for. So of course combine those two and we get 0.3 kilograms, and then to get that alone we're going to divide both sides by 0.3 kilograms. 0.98 divided by 0.3, and I get 3.26 repeating. So then that gives me 3.26 repeating, and then we have newtons divided by kilograms. Well, remember, newton is a kilogram meter per second squared, and we're dividing that by kilograms. So the kilograms here are going to cancel out, and we're going to be left with meters per second squared, which is what we expect for an acceleration. So good thing that worked out. And then we had 2 sig figs originally on both of these, so I need to round this one off to 2 sig figs, and so then I get 3.3 meters per second squared is equal to the acceleration. So I've taken this diagram and redrew it over here, cleaned it up, and added in our numbers. So I put a 30-degree angle from the horizontal here and a 60-degree angle from the horizontal here, and called this one 25 kilograms. Now, a lot of times in problems like this, you're given the tension force of one and asked to solve for the tension of the other, and that is a lot simpler than what we're going to do here. What we're going to do here is going to end up involving some substitution. So it's doable, but it's a little lengthy. So let's take a stab at it. If this thing has a mass of 25 kilograms, then we know that the force due to gravity is 25 times 9.81, and that would be, of course, newtons. I should have had my units in there with me. So 25 times 9.81, and I get force due to gravity is 245.25 newtons, which we're going to round off to 245 newtons because 3 sig figs. So that's our force due to gravity, and so now what we know is that the forces in the x direction and in the y direction have to be equal. So if I call this tension 1 and this one over here tension 2, or I could call it FT1 and FT2. I'm going to clean it up just a little bit by using just T1 and T2 here. Then we know that T1 in the x direction has to be equal to T2 in the x direction, because this thing is stationary. If it's stationary, these two have to be equal in size, opposite in direction. We also know that with the y components here of these two, that T1 in the y and T2 in the y direction are equal in opposite direction to the weight. So 245 newtons, or the weight. And so we've got two different groups of variables here, and so we end up having to do substitution when we have that. But we can solve for the tensions here. So if we draw out these triangles here, then this is T1y and this is T1x, and this over here is T2y and T2x. And so now we have each of those. and we can solve for these values. So since we know we want to know this one, that is the adjacent, and for adjacent here we're going to end up using the cosine function. And so cosine of 30 degrees times by t1 is going to be equal to t1x, and t2 cosine of 60 degrees is going to equal t2x. And if that was too big of a jump for you here, cosine of 30 is equal to t1x over t1, because it's adjacent over hypotenuse, so adjacent hypotenuse, and then I multiplied both sides by that to get t1 cosine 30 is t1x, identical process for t2 here. Anyway, we've also stated that these two are equal to one another, so now we know that t1 cosine 30 is equal to t2 cosine of 60, and we can solve for cosine of 30 and cosine of 60 here. So cosine of 30 is 0.866 t1, and that's going to be equal to, that one should be 1/2 0.5 t2. And so then I can combine my numbers, and I personally prefer to do bigger divided by smaller, so 0.866, probably should take the time to get that and get the full decimal, but I'm going to go shortcut here. And I end up with 1.732 t1 is equal to is equal to t2. That's all the further we can go right now. We're going to have to come over here and work with the y direction now. So in the y direction here, we have that t2 in the y direction is going to be the sine function this time, and sine function here for t1. So it's going to be sine of 30, t1 sine of 30 plus, excuse me, yes, that's correct, t2 sine of 60, because this here is t1y and this here is t2y. Same reason as here, we just replace cosine with sine, and then we're replacing our x with our y, and then it's the same process. We end up multiplying both sides by the tension, and so then our t number y is equal to t number times sine of that angle. And that's equal to 245 newtons. And so now, we again can solve for the sine of each of these. So this one here should come out to be 0.5 this time. So 0.5 t1 plus sine of 60 should come out to be the 0.866. T2 is equal to 245 newtons. Now, I know it's very tempting to try to do something with these numbers and that newtons there, but we can't because they're tied to a variable and we have to get rid of the variables, and we can't get rid of the variables yet. But what we can do is we can replace T2 here with T2 from here. And so we're going to do that substitution, and when we do that, then we have 0.5 T1 plus 0.866 times T2 is 1.732 times T1 is equal to 245 newtons. So now I can do this ugly combination here where I take this number that I still have in my calculator times by the 1.732, and that gives me, look at that, that's so close to 1.5. You know what, we're going to call it 1.50 T1, and 0.5 T1 is equal to 245 newtons. So now we can combine those two. We end up with 2.0. T1 is equal to 245 newtons. And you can see here now if we have 245 newtons, we're going to divide both sides by 2. And we get that T1 is equal to 122.5, and let's see here, we had 3 sig figs originally, so we're going to call that 123 newtons. So T1 is 123 newtons. Fg we solved for previously, and so then the only one of these forces we have left then is T2, and T2 we know is equal to 1.732 times T1. So we have T1 now, so 1.732 times, I'm going to use the full one here, 122.5 newtons is equal to T2, and then multiply those out, and we get 212.17 newtons is equal to T2, which we're going to round off to 212 newtons. So there's T1, T2, and we've already stated it here, but the force due to gravity, and that's all of our ones. Now, this was ugly, without a doubt, and it is lengthy, but normally what will happen is you'll be given the tensions instead, or you'll be given one tension, and then you'll be asked to calculate the other. And from there, it's doing the reverse trig processes using the inverses, and you'll figure out the x component here, and then if you know the x component here, then you can solve for the x component there, and then if you again, you can solve for the y component here, and if you know the y component here, then you take the weight minus that y component, and this one has to be the rest of it, and so then you can solve for the y component there, and then once you have those two, then it's just Pythagorean to get that one. Still not slow, it's still a multi-step process, or excuse me, still not quick, it's still a multi-step process, but it is solvable, and it's a lot easier than doing this kind of substitution. You don't have to do that kind of substitution when you're taking the result and then turning it and resolving it, instead of taking the resolutions and coming up with a result. So now we're ready for the famous ramp problem. And solving this one is a little odd, but what I've done here is I've given us the angle of 25 degrees, should match that one, and then I said let's pretend the box here is 5 kilograms. Now we of course know that we can solve for the force due to gravity. We've done that several times already. It's m times g, so that's 5 kilograms times 9.81 meters per second squared, and so then that's going to give us 49.05, and you know what? I didn't do a good job with sig figs here, so let's pretend for a moment that this is 3 sig figs, and we'll call it 49.1 newtons. So that's our force due to gravity here. So now what we need to do is solve for this, and we do an odd trick here, and that is we're going to change our normal Cartesian coordinate plane. So I brought this in here transparent to show you kind of why. So normally, of course, we have our y-axis there and our x-axis there, and you can do that, but if you end up doing that, you'll notice the only thing that we have actually on one of these axes is the force due to gravity here, and then that means we end up having to do trig on both the force of friction and the normal force here, which I did not label. But what we can do is, instead of doing that, we can rotate our coordinate plane. And if we do that, notice now we only have trig on one of these. We only have one that's not directly on an axis, and so the force of friction is directly on the x, and the force normal is directly on the y, and so then what we can do is we rotate this. So we normally rotate this, and when we do that then, we end up having to consider these vectors here. And if this thing is at rest, then we know that the y component of the force due to gravity here is going to be equal to the normal force, and we know that the x component here is going to be equal to the frictional force. And so then we can solve for that. Now from there, we're taking advantage of the properties of similar triangles. And so it turns out that if this here is 25 degrees, that this one here is also 25 degrees, and this one here is 25 degrees. And so the odd thing with this then is now we have our triangle here that we're going to focus on. I'm actually going to come in here just to emphasize it. Not that we couldn't use the other triangle, but this is just the one we generally use, the one that's going down here. And then that there is our right angle, which means this force due to gravity that we've already solved for, that is now our hypotenuse, you'll see. And so then we're really dealing with a triangle like this, where we know those parts of it. And so then to get the force of gravity in the x direction, that is going to be a sine function, it looks like, because we're going to have opposite and we're going to have hypotenuse. And so then we know that sine of 25 is equal to sine of 25 is equal to the force of gravity in the x direction over the force of gravity. And of course we know that force of gravity is 49.1 newtons. So then F of g x is equal to 49.1 times sine of 25. And we can work through that again, but I hope you can follow and trust me that Fg of y then is equal to 49.1 cosine of 25. And so then we're going to do those into the calculator here. So this is the 49.1 here times by sine of 25. Oh, poo. And I get 20.8 newtons when I round that off to 3 sig figs. And then if I come up here and I replace that with cosine of 25 instead, I get 44.5 newtons. And so now we know that the F in the x direction is equal to this. And if the F in the x direction is equal to that, then this one has to be equal in size to this one here. So now we know the force of friction is 20.8 newtons. And if we know the force in the y direction here is this, 44.5 newtons, then we know the normal force is also 44.5 newtons. And so now we've solved for all three of our components that we had originally. And if the rock was sliding down, you'd have to be given the frictional force or given the coefficient of friction to solve for that. And we'll do some example problems of friction calculations later on. Anyway, that finishes up these calculations, so be sure if you have any questions that you let me know.